Hello, everyone. My name is Isaac, and I'm a PhD student at U Laval. And today I have the pleasure to show you some results of my PhD, especially focus on the P-T-t deformation-fluid evolution of the Pontiac and its implications for gold mineralization. So it's now known that most orogenic gold deposits were formed at the late stages of the superior craton stabilization, around 2.7, 2.6 billion years, and they are close in time with the metamorphic evolution of the metasedimentary subprovinces here, some Quetico, Nemescal, and most important for us, the Pontiac. So this raises the questions, why did this somehow the metasedimentary subprovince contribute to the formation of orogenic gold deposits? As Taylor mentioned here, we chose the Pontiac because Pitcairn and co-authors have interpreted the Pontiac as a source of gold that the metasediments could have produced over 250,000 tons of gold, which kind of represents 3% of the estimated resource on the Abitibi gold camp. This is the research objectives for us. It's first defining the P-T-t deformation-fluid evolution, better understand the Neoarchaen tectonics and the impact of the regional fluid generation in the circulation of gold endowment. And more specifically, I'm going to try to establish the time of metamorphic fluid release and its temporal correlation with the gold mineralization in the Abitibi gold camp. I'm going to try to quantify the volume of metamorphic fluid release during prograde dehydration reactions. So here we're looking for other elements like sulfur, carbon, and other metals that are going to be released during these reactions. I'm going to try to determine the key metamorphic reactions responsible for fluid production. So here we're kind of looking for, especially for hydrophases like muscovite, chlorite, and also in looking for pyrite and pyrrhotite reactions. So ideally, we want to look here in a PT diagram. We want to looking for the gold fluid window. What's the best conditions for during prograde metamorphism to have this gold fluid window? So the approach was include mapping the metamorphic isogrades in zones, petrological microstructure analysis, raw rock mineral chemistry, phase equilibrium modeling of representative samples, and we also got some agents, UPB monazite and zircon agents and lutetium, hafnium, garnet, dating of metamorphic reactions and fluid release. Just to give you a little bit of context here, we have the Pontiac subprovince. It's mainly represented by basement rocks, the TTG gneiss suite here, that west part and the south part, sanuctoid suite and nest-type granites in the central portion. The Pontiac group mainly occurs in the north part of the area. We have a thick turbiditic sequence with concordant comatiatic and basaltic flows in the area. We know that the maximum depositional age is around 2682 million years. And we also know that we have a Barrovian prograde metamorphic age around 5657 million years based on dating, lutetium dating on starolite zone rocks. So we choose this area here because it preserves a complete Barrovian sequence. So the first step was to remap the metamorphic isogrades in the area. So from north to south, we see an increase of metamorphic grades. So we starting from the biotite and goes to the sillimanite zone, passing to the garnet, starolite, and the kyanite. Unfortunately, we didn't find samples from the kyanite zone, but some works have been reporting. As Taylor mentioned here, we have these two deformation phases in the area. First, S1 foliation includes subvertical to vertical northeast trend cleavage that's parallel, subparallel to the bedding planes. We have a second foliation defined by vertical east-west trending crenulation cleavage. And here we have this relationship that Taylor mentioned, shown in his presentation. We have the SE2 as a crenulation cleavage here, and the S1 as a microarlingtons. And here we have the relationship between the F1 and the F2 here, showing the fold axis for F1 and F2. And now with a better knowledge of the deformation phase, we try to correlate the fabrics we observe and with the mineral growth. So we're able to determine that the peak metamorphic assemblies were developing during and after D2 deformation phase. And here we have that LASPMS maps of chromium and garnet here. This is important for us because chromium is immobile during prograde metamorphism. So here we want to see the relationship between the garnet growth and the fabric. This would be important when you're dating garnet. So what we can see here that garnet across all the metamorphic zones appears to grow after the main foliation. Here, we use this AFM diagram to investigate how the mineral assemblies vary as a function of a whole rock compositions across the metamorphic zones. So here we select some representative samples from the across all the metamorphic zones, 2 samples for the garnet zone, 2 samples for the saurolite zone, and 1 sample for the sillimanite zone. Here we have the different steps that we took to retrieve the peak PT conditions from this rock. So first we use the whole rock data. We choose the compositional system, and then we calculated the isochemical PT phase diagram. We also estimated the model proportions of the major phase using micro-XRF and petrography. And also with the probe data, we got the mineral compositions that we use. So here we have this isochemical PT phase diagram. So the first thing you want to look here is if we're able to reproduce the same thing we observe in the thin section. So if the answer is yes, we can then start thinking about the mineral compositions and about the major, the model proportions to try to establish the peak PT conditions. So here we have the model proportions of the major phase, and here the isoplats that we calculate with the composition. So if everything intersect here, in these 2 cases, we can then estimate the peak PT conditions. Another thing we used was the grossular contents from garnet quartz ring, and you use the grossular contents because calcium has a slow diffusion rate, so we could estimate the establish the PT vector that these rocks follow. So in that case, this was the approach that we apply for most of our samples across all the metamorphic zones. And this was our paper recently published, and that we show all these phase diagrams. I mean, show everything. So if you're interested, you can check it's open access, so you're able to download and take a look. Here, we also have date garnet to constrain the time of prograde metamorphism. We have obtained an age of 26, 15, 7 million years across all the metamorphic zones from the garnet, staurolite, and the sillimanite zone, which is compatible with the previous published age around this 26, 15, 7 million years close to Valdor. And here we have the lutetium maps for the garnet, the staurolite, and the sillimanite zone. We can see here preserved growth zoning with some oscillatory zoning, so maybe indicated that we have a minimal diffusion. So we are confident that the ages that we got from garnet is we constrain the time. We are constrained the time of prograde metamorphism. As another control of the metamorphism, we also date monazite and zircon for the sillimanite melt zone rocks. We got an old age, around 26, 60, 67 million years for the monazite, and a young age of 26, 45 million years. So this is the main outcome of our work. We try to constrain the P-T-t paths across all the metamorphic zones. So we're able to identify the 3 types of PT paths. a load heating path for the garnet zone rocks, then where rocks reach conditions of 8 kilobars, as Taylor showed in his presentation, around 585 Celsius. We have the starolite zoning with a pressure of 6 kilobars and 620 Celsius. And we have the sillimanite zone around 6 kilobars and 700 Celsius. Here we establish the peak conditions. What we can see here, the garnet grew at the same time across these 3 different metamorphic gradients and across 2 different thermal gradients. So with garnet, we got colder gradients around 20 Celsius per kilometer. And for the starolite zone and the sillimanite zone, we got around moderate gradients around 33 Celsius per kilometer. So one of the interpretations we have is that the subsolids monazite and garnet that we date to 2667 and 2657 million years, it constrain the time of prograde metamorphism. In that young age here, we have obtained for suprasolid zircon overgrowth, constrain the time of high temperature cooling. So this was the solid foundation we have before we start to constrain the fluid evolution. So along these P-T paths here, we want to see how the fluid evolves here and what reactions we have, important reactions we have that release fluid into the system. So we're gonna try to calculate across the 2 different gradients, we're gonna try to determine what's the best pressure and temperature that fluid is released along this P-T path here. So in one of the important things we wanna considering is the sulfur liberation and when you try to model in the fluid. And the most important reaction that we need that releases sulfur during prograde metamorphism is the pyrite to pyrrhotite desulfidation reaction. So here we have this generic PT diagram that's where we have Tompkins in 2010 constrained the sulfur window that we expect to have across a generic to PT path here. So we want to test this with real rocks. We want to test with our rocks in a much more complex system, compositional system, if we can produce sulfur along a PT path. And one of the important things for us was to document the pyrite and pyrrhotite reaction across the metamorphic zones. So our group also published this paper here that we characterize the chemical isotopic compositions of pyrite to pyrrhotite across the biotite, from the biotite to the sillimanite zone. So what we observe is a decrease of pyrite when we increase pressure and temperature conditions here until we have in the sillimanite zone, we have only pyrrhotite. So the idea, can we model this what you observe, the textures you observe? If you didn't answer yes, let's see. So the first thing we tried to calculate again was a PT isochemical diagram, but this time we add sulfur to the system. So we're increasing the complexity of the PT diagram here. And the first thing to do is, can we observe pyrite and pyrrhotite in that sample? If yes, we can then determine here, constrain the peak, the field of interest here. And then we can use the peak previously established PT path to evaluate the evolution here across the pyrite and pyrrhotite reaction. And here we have also important reactions here, because the peak we got here, we try to extend to see the processes we have with chlorite out and muscovite and starolite out, because starolite in, because we need to understand this hydrophase, how the fluid it's being released across these reactions. Another thing was important for us was we need to make some adjustments in the oxidation state of our sample, because now we're adding more, we're adding the pyrite and pyrrhotite to the equation. So we need to stabilize the ferric iron components of our diagram here. So we created this TXO diagram, trying to get an average value of oxygen for what we observe in the thin section. So here we can, if we find pyrite and pyrrhotite in the garnet zone rocks, this is the range of oxygen values we can use. And also it's important to establish the conditions for the oxides as well. So along this PT path here, we try to fractionate the fluid. And this is only for the garnet zone rock, and we try to fractionate in 500 steps with increments of 0.0 Celsius and 2.2 bar per step. And here we have the HOS cumulative fluid loss of HOS, and here we have the cumulative loss of sulfur. Here we increase the temperature and the pressure here. We used also the starting book composition. It's the same as the fixed book composition, and we use a rock porosity of 1 volume % of fluid through the PT path, which is consistent with a metasedimentary rock porosity. So as you can see here, we have this jump in both cases of fluid and sulfur in the system here. It is mainly attributed to the breaking down of muscovite and chlorite that's releasing, fluid into the system, and also the breaking down of pyrite and pyrrhotite here at the low temperatures. And here we have an estimative here of the mole fraction of fluid here that we got at a specific temperature. It's around 0.00056, which is a small value. But when we convert this value to understand the cumulative sulfur loss, we end up calculating 10.4 million kilogram per cubic kilometer, and for these conditions here. So again, we raising this question: how much gold and other metals can be mobilized from the Pontiac, potentially to contribute to gold endowment in the Abitibi? We don't have the answer yet, but we're still working on. The next steps will include the fluid speciation that we already done some calculations, and also I'm going to try to calculate the cumulative loss of sulfur in the starolite zone rocks, because here we're considering high pressure. So here, just to wrap it up, what we have. So in 2667, 2657 million years, we have the prograde metamorphism, subsolids monazite crystallization, garnet growth, and the main fluid generation that we calculated here. 2645, we have this regional cooling, suprasolidus zircon overgrowth, and it's correlated to the main mineralization event we observe in the Malartic Valdor camp here. And we got to this age as well from Herzog that is attributed to gold remobilization. So if you're considering a model to explain how the fluid is evolving, we have this deep layer model by Stu, where the fluids produced at depth that are undergoing prograde devolatilization reactions, it can form or deposit at shallow levels and along the retrograde PT path due to erosion dripping of lift. In some cases have demonstrated that in some regions that could take 20, 30 million years from the fluid to be released to the deposition of gold in other orogenic other deposits. Thank you very much.